Hi, Year 9 students. I'm Norman Wildberger. Today we're going to have a look at fractions. It's a review. It's a very important topic for Year 9 students because it's going to form the foundation for moving towards algebra. The operations of algebra are very parallel and almost the same, really, as operations with fractions. So one of the difficulties with fractions is that there are quite a lot of different ways of looking at them or interpreting them. Eventually we want to do arithmetic with them, so we're going to be doing arithmetic like this, and I hope it's somewhat familiar. 1/2 plus 3/4 is 5/4. We can multiply fractions. 2/3 times 5/8 is 5/12. And I'm going to be reviewing this kind of arithmetic in today's video and also the next one. But before we do that, I think we have to first get a sense of what fractions are and how to visualize them. So we want to have a mental image or geometrical understanding that links up with the arithmetic of the numbers that we're writing down. So let's start with the number line that we talked about in our last video, with the integers 0, 1, 2, 3, -1, -2, and so on, equally spaced, going on in this direction and this direction. So what we want to do with fractions is we want to increase our number system so that we can deal with numbers which are in between the integer values. And it's probably best to start off by concentrating on this basic interval first, subdividing the interval between 0 and 1 in a regular kind of way. Now there's lots of ways of subdividing that into a regular way, because we could divide it into, say, 2 equal pieces, or into 3 equal pieces, or 4 equal pieces, or 29 equal pieces. Okay. And the language of fractions is really designed to help us do that. So let's start with the simplest kind of division, where we divide 0, 1 into 2 equal pieces. So we can do that with this marker right here that divides it into 2 equal pieces. And then this number is going to be called 1/2. It's the result of dividing 1 by 2. If we had divided the original interval into 4 equal pieces, well, then you can see the 4 pieces here. 1, 2, 3, 4. So this marker here makes this thing 1/4 of the whole thing. We've divided 1 by 4. We could continue, so we could divide the interval into 3 pieces, equal pieces, or maybe into 7 equal pieces, or maybe into 30 equal pieces, and then we would get the smaller fractions, 1/3 or 1/5 or 1/30. So that's the basic operation. We're dividing the interval 0, 1 into n equal pieces. Then each piece has size 1/n. Well, once we have this, say, 1/2, then we can use that as a kind of a new kind of unit to mark off also other points along the line. So if this is going to be 1/2, then if we take this segment and multiply it by 2, we're going to get 1. If we take 3 of them, 1, 2, 3, then we would get to this point here. So this is 3/2. If we take another 2, making 5 of them, 1, 2, 3, 4, 5, then we would get 5/2. If we went in the negative direction, we would get -1/2. This is the way we can scale. Once we have one of these sort of unit fractions, we can take multiples of it to create other ones. That's a good place to start. Some simple fractions created from the interval 0, 1 just by subdividing it into n equal pieces. In general, we get the fraction 1/n, which we'll generally write with a sort of a slanted line there, at least at first. The fractions of the form 1/n, such as 1/2, 1/3, 1/4, 1/5, are the simplest kinds of fractions. And they're the ones that have been around historically for the longest time. the ancient Egyptians used these kind of fractions in their arithmetic. So when they were building the pyramids, they did use fractions like this. Fractions like this are also called unit fractions because there's always a 1 up at the top. And here I've taken the interval 0, 1 and kind of blown it up a little bit so we can see it a little bit better. And halfway, that was the fraction we called 1/2. And if we divide this into 3 equal pieces, well, does that look like roughly 3 equal pieces? 1, 2, 3. Maybe I'll mark the other one as well. Maybe roughly about there. Okay, so from here to here to here to here, 3 equal pieces. Then that number there is 1/3, because it's what you get when you take the big interval and divide it by 3. 1/4 would be around there, 1/5 around there, and as we increase the denominators, the fractions are getting closer and closer to 0. Okay, so those are Egyptian or unit fractions, and they are the basic ones that we start with. Then we want to consider more fancier fractions, maybe composite fractions, where we consider general numerators and denominators. So 2/3, what does that mean? Well, we're going to think about 2/3, or 2/3, to mean 2 times 1/3. So we're going to think about this thing in terms of the unit fractions that we've just been talking about. So 2/3 means 2 copies of 1/3. In other words, 1/3 plus 1/3. So we can also write this as 1/3 plus 1/3. So there's 1/3, and another copy, 1/3 there, would make this 2/3. Similarly, 5/4 means 5 times 1/4. Let's see where that would be on our scale. So here's 1/4, obtained by dividing the interval into 4 pieces. So if we take 1/4 and we take another 1/4, we would get a half. So this half also is equal to 2/4, because it's 1/4 plus 1/4. And if we added one more, we would get something over here, which would be 3/4. We add another quarter to that, we would get 1, which is 4/4. Let's think about that for a second. Okay, so 4/4 means 4 times 1/4. 1/4 is what we got when we divided the interval into 4 equal pieces. And if we take 4 of those, well, that means we get the whole interval back again. So 4/4 is the same as 1. There's nothing special about 4 that way. 3/3 is also 1. 2/2 is also 1. 6/6 is also 1, and so on. All right, what about 5/4? Well, that's 5 times 1/4. So far we have 1, 2, 3, 4 of them. If we add one more, then we're out here somewhere, and that would be 5/4. So we can get more and more fractions of the form 6/4, 7/4, 8/4, and so on, just by adding a quarter, etc., to wherever we are. How about -2/5? Well, that means -2 times 1/5. The 2 is just like multiplying by 2. What's 1/5 plus 1/5? And the minus sign changes the sign. So let's see where this number is, where -2/5 would be. Here is 1/5, and then if we added that to itself, 2/5 would be somewhere around here. And then -2/5 would have to be the reflection of this in 0, which would be almost on the edge here somewhere. So that would be -2/5 somewhere around there. All right, so we're ending up with quite a rich possibility for creating lots of points by taking the unit fractions, or the Egyptian fractions to start off with, and then multiplying them by certain numbers, which end up in the numerators, giving us larger versions of those unit ones, scaling them up, adding a lot of them together. Okay, there's a natural connection with division, which we now want to also talk about. Of course, division is the fourth operation in arithmetic. Addition, multiplication, subtraction, and division are the usual order of the operations. Division is the fourth one, and it's also almost surely the most complicated one. It's in some sense the opposite of multiplication, sort of the inverse operation, sort of undoing what multiplication does. So let's just talk first of all about division of ordinary natural numbers or integers. So if we have 15 divided by 3, well, we all know that that's equal to 5. What does that actually mean? What does it mean when we say 15 divided by 3 equals 5? Well, actually there's two possible things that this can mean, and they're subtly different. So one thing that it could mean is that the number of 3's that fit into 15 is 5. So one way of interpreting what 15 divided by 3 is, we're asking how many 3's can we fit into 15? So we have 15, and we want to write it as 3, another 3, another 3, another 3. How many 3's can we fit into 15? That's one interpretation of what 15 divided by 3 is. Another interpretation, which is different, is the question, if we divide 15 into 3 equal pieces, how many are in each piece? Okay. Again, we get the answer 5. We divide 15 eggs between 3 people. Each person is going to get 5 eggs. That's a different question from the first one, which is asking how many groups of 3 eggs can we extract from all 15. Okay, so these two interpretations of what this means corresponds to the two products or possible ways of multiplying 5 and 3 to get 15. We can think of 15 as 5 times 3 or as 3 times 5. Remember, our interpretation of this was 5 times 3 means 5 groups of 3. It means 3 plus 3 plus 3 plus 3 plus 3. 3 plus 3 plus 3 plus 3 plus 3. 5 groups altogether. And this one, 3 times 5, means 3 groups of 5. 5 plus 5 plus 5. So let's make an agreement about what this means. Let's choose one of these interpretations so we have a consistent way of thinking about what division is going to mean for us. And there's no right or wrong way here. It's just one way that's convenient for us to be consistent in terms of thinking about what division is. All right, so let's agree that when we write 15 equals 3 times 5, that's equivalent to 15 over 3 equals 5. In other words, when we asking what does 15 over 3 mean, we're going to choose the second interpretation. That if we divide 15 into 3 equal groups, each piece is 5. Because here, this statement is saying that 3 groups of 5 makes 15. 5 plus 5 plus 5, so 3 groups of 5 makes 15. So if we divide 15 by 3, we're asking, if we cut up 15 into 3 pieces, how many are in each piece? It's 5. All right, so for example, we'll think about these two equations as being essentially equivalent. 21 equals 7 times 3. 21 is 7 groups of 3. So if we divide 21 by 7, if we subdivide it into 7 equal groups, then each group will have 3 pieces. So geometrically on the number line, which is how we're liking to think about numbers now in grade 9, here is 15. Okay, 15 is a position on the number line. And it's 3 groups of 5. 5 plus 5 plus 5. And so when we're saying 15 divided by 3 is 5, we're saying what happens if we take this interval of length 15 and we divide it into 3 equal groups. That's what we've done here. We've divided into 3 groups. 1, 2, 3. And we've seen that each group has 5 elements. So that's how we're going to interpret division. We have an interval. We're going to divide it by 3 means cut it up into 3 equal pieces and then ask how many are in each piece. Over here, for example, same thing. Here is 21 on the number line. When we say 21 over 7 equals 3, what we mean is that if we take this interval and we divide it by 7, if we cut it up into 7 equal pieces, then each piece is going to have 3 in it. 3, 3, 3, 3, 3, 3, 3. 1, 2, 3, 4, 5, 6, 7 groups of 3 make 21. So this is the inverse of this statement. The two statements are pretty well the same. 21 equals 7 times 3. Okay, in that case, 21 divided by 7 equals 3. So hopefully you can see how to go from a multiplication like this to a division, or from a division like this to a multiplication like that. Okay, that's all well and good. So that's division with natural numbers or integers. So how do fractions fit into the story? Okay, so when you're learning division in primary school, you learn that one number is not always divisible by another. So yes, we can take 15 and we can divide it by 3. We get an answer, namely 5. But if we try to divide 15 by 4, it's not so easy. So a primary school student would say, well, you can't divide 15 by 4. But then as you get a little bit more advanced, you realize that you can, in fact, divide 15 by 4. But the answer is not a number, it's a fraction. So we have to understand how fractions arise as the results of division of ordinary numbers. So here's a good example. Suppose we have the question, what is 4 divided by 3? This horizontal line means division. We have the number 4 divided by the number 3. So when you're in grade 3 or something, if I asked you what's 4 divided by 3, you'd say, oh, it doesn't divide. Okay, but you can still do it if you have some fractions to help you. And to make this very explicit, let's have a look at a concrete example, a real life example. So the 4 is going to represent 4 chocolate bars. And the 3 is going to represent 3 friends. And the 3 girls, A, B, and C, maybe Anne, Barb, and Kathy. All right. And so the question is, how are we going to divide 4 chocolate bars amongst 3 friends? Well, we want to do it in an equal way so that each of the 3 girls gets the same amount. Okay, so there are 2 ways, at least, of thinking about this problem. And I suppose that most of you, if actually presented with this dilemma, would answer it this way. Well, there's 3 girls and there's 4 chocolate bars, so why doesn't each girl, first of all, take a chocolate bar? So A can get this one, B can get this one, and C can get this one. And then we have this 4th chocolate bar left over, and so we need to divide that up equally amongst the girls. So why don't we just get a knife and cut it into 3 equal pieces and give each of these pieces to one of the girls. So that way each girl gets a whole chocolate bar plus a third of a chocolate bar, which we can write like this, 1 1/3. And so we can say that 4 divided by 3 is 1 1/3. When you divide 4 by 3, you get 1 1/3. This kind of number is sometimes called a mixed fraction because there's really a plus sign in here that's not being written. So it really means 1 plus 1/3. And it's mixing together natural numbers and fractions. Okay, but there's another strategy for dividing up the chocolate bars. Okay. Another strategy is to take each of the 4 chocolate bars and divide each of them up into 3 equal pieces. So we divide the first chocolate bar into 3 pieces, the second chocolate bar into 3 pieces, the third into 3 pieces, and the fourth into 3 pieces. And then each person gets 1 piece from each of the chocolate bars. That's also fair. So A gets this piece, this piece, this piece, and this piece. And so we could then say, well, 4 divided by 3 is 1/3 plus 1/3 plus 1/3 plus 1/3. 1/3 plus 1/3 plus 1/3 plus 1/3. And we've just said in the previous video that if we have 1/3 plus 1/3 plus 1/3 plus 1/3, that's what we're going to call 4/3. 4/3 is 4 times 1/3, so it's exactly that. Which of these methods is superior? Well, it's hard to say. This was certainly less work. But if the chocolate bars are perhaps not quite the same size or the same flavor or something, maybe this is a fairer method. But anyway, we can agree that the results of the 2 methods are the same. That 1 1/3 really is the same as 4/3. This fraction and this fraction, they're just 2 different ways of representing the same quantity. And so we've arrived at this seemingly kind of obvious fact, but it is not entirely obvious. It's worth pointing out that if we have not just 4 and 3, but if we have 2 natural numbers, say m and n, if we divide m by n, then we're going to get the fraction m over n. So this line here represents a division. We're dividing this natural number by this natural number. This line here is alerting us to the fact that we have a fraction. This is the fraction m over n, which means m copies of 1 over n. 1 over n plus 1 over n plus 1 over n, m times. So we've seen that in the case 4/3. If you have 4 chocolate bars and you divide those into 3, then each piece is 4/3 of a chocolate bar. And exactly the same reasoning shows that if you have m chocolate bars and you have n friends, you divide the m chocolate bars into into your n friends, each is going to get m over n. So this is a connection that's important to point out, that the fraction 4/3 can be interpreted now in different ways. You can think about it as being 4 copies of 1/3. That's how we started thinking about it. But you can also think about it as being what you get when you divide the number 4 by 3. So it's the result of an arithmetical operation on natural numbers whose answer is a fraction. All right, so we did say we were going to try to think about fractions in terms of a number line, not necessarily pieces of cake or chocolate bars. So let's have a look at what the same question just looks like on the number line. There's the number line. 0, 1, 2, 3, 4. Okay. So suppose we wanted to calculate 4 divided by 3. So we're taking the interval 0 to 4, and we want to divide it by 3. Okay, so how do we do that? Well, here is what we get when we do that. We end up with 3 segments. Here they are right here. Okay, and each one of them is 4/3 long. Where's 4/3 on our picture? Well, we get 4/3 by starting with 1/3. Okay, so we're taking the interval 0, 1, which is smaller now than it was before, and dividing it into 3 equal pieces. Because we're talking about thirds now. Okay, so that's the number that we called 1/3. And that's 2/3. That's 3/3. 4/3. 5/3. 6/3. Same as 2. 7/3. 8/3. 9/3. 10 thirds, 11 thirds, 12 thirds, 13 thirds, and so on. And what we're saying is that when we take this interval 0 to 4 and we divide it by 3, we're getting 4 thirds. Exactly from here to 4 thirds is 1/3 of the way along. Let's just check that. If we take that and we double it, we go from 4 thirds up to 8 thirds. If we add another copy, we go from 8 thirds to 12 thirds, which is the same as 4. So yes, indeed, if we divide 4 by 3, we get 4 thirds on the number line. And we can also see that how to rewrite the 4 thirds in terms of a mixed fraction, because the 4 thirds is a little bit bigger than 1. It's exactly 1 plus 1/3. So we can see the mixed fraction aspect of it on the number line, telling us sort of what the nearest integer is below it. So for example, let's say we have 11 thirds and you want to immediately write down what that is as a mixed fraction. 11 thirds will be 1, 2, 3 plus 2 thirds. Remember, each one of these intervals is a third. 1/3, 1/3, 1/3, 1/3, 1/3. So 11 thirds is 3 and 2 thirds. Okay, try to figure out for yourself, what is 7 thirds as a mixed fraction? Just looking on the line. Do you all get 2 and 1/3? Good. Okay, so let's take a bit of a larger example, same kind of thing. Let's divide 23 by 5. We have the number 23. We want to divide it by 5. We want to know what is the result of that division. On the number line, well, we have to go a little bit further. So there's 5, 10, 15, 20, 25, 23 right there. So we're asking, okay, if we take that strip from 0 to 23 and we divide it by 5, how big is that? Well, it's roughly this big. Okay, that's about a fifth. 1, 2, 3, 4, 5. That's roughly somewhere in there. But where is it exactly? Well, let's do an actual division. Okay, I'm going to remind you about long division. Relatively simple one. Okay, let's divide 23 by 5 using long division. We're not going to use a calculator. We're going to try to stay clear from calculators. I want you to always be writing with pencil and paper or pen and paper. Very important tool for you to have beside you when you're doing mathematics. Teachers, make sure your students have access to pen or pencil with some paper where they can make some calculations without relying on calculators. Crucial. Okay, how do we do this long division? Well, we want to know how many 5s go into 23. And knowing our multiplication table, 2 times 5 is 10, 3 times 5 is 15, 4 times 5 is 20. It's getting close. 5 times 5 is 25. That's too much. So 4 times 5 is a good guess. So we write a 4 there. And 4 times 5 is 20. We take those 4 5s away from 23, and what's left is 3. And we ask, well, how many 5s fit into 3? And the answer is, well, we can't fit any more. That's just the remainder. So in primary school, you would say that the answer is 4 with a remainder of 3. Well, the analog in terms of fractions is that you're getting the number 4 and 3/5. So if you think about 23 chocolate bars and 5 friends, okay, then what you have is each friend is going to get 4 chocolate bars. 4, 4, 4, 4, 4. That accounts for 20 chocolate bars. Then there are 3 left over. And you're going to have to take those 3 chocolate bars and divide them up into 5 equal pieces. So each person is going to get 4 and 3/5 of a chocolate bar. Okay, but what is 4 and 3/5? Another way of saying that is it's 23/5. Or 23 times 1/5. So to understand this in the same way as I did over here, we would really want to subdivide each one of these intervals into 5s. Okay? I'm not going to be able to do that in a very accurate way, but kind of imagine that I'm dividing each one of these into 5 equal pieces with 4 little lines. Okay? Each one of these is 1/5. Okay? So that's 1/5, 1/5, 1/5, 1/5, 1/5. 5 of them make 1. So where are we once we have 23/5? Well, there's 5 of them, another 5, another 5, another 5, makes 20 of them over there, and 3 more will be 1, 2, 3, 4. We have to go 3 of them, 1, 2, 3, so it'll be right there. A little bit hard to see, but that will be 23/5 right there. And it's just the fraction that you get when you take 23 over 5. So we've had to do the division in order to rewrite it as a mixed fraction, which helps us understand where it is. So until you've done the mixed fraction, you don't really know where 23 over 5 is. But after we've done the mixed fraction, we know that it's 4 and a little bit. So it's somewhere between 4 and 5. Okay? There it is right there. All right, so that's good. We've covered a fair amount of material. This is going to be the last topic here in this little review today. We're going to talk about equivalent fractions, and then we'll have a little bit of practice. Okay, so one of the things that makes fractions a little bit tricky is that there is often, well, there's always, more than one way of writing down a fraction. A fraction has different possible names. And I want to illustrate that with 2 different number scales. 0, 1, 2, 3, 4, 5. And here is person A, and person A has subdivided their scale into thirds. So they've taken the interval 0, 1 and divided it into 3 equal pieces with these lines. And they've done that with each interval. So each one of these separations is 1/3. And so then they have names for each one of these fractions. So that's 1/3, 2/3, 3/3, same as 1, 4/3, we haven't marked it, 5/3, 6, 7, 8, 9/3, 10/3, 11/3, 12, 13, 14, 15/3, same as 5. Also we could go in the negative direction, so that would be -2/3. And person number B has taken that same number line, but has had a more refined subdivision. Person B has decided to subdivide each fundamental interval into 6 equal pieces, not 3. Okay? So they've done a little bit more work. 1, 2, 3, 4, 5. So now there's 1, 2, 3, 4, 5, 6 equal pieces between 0 and 1. So that means each one of these is what we would call 1/6. That number right there is 1/6. Maybe I'll mark it here, perhaps there, 1/6. So that's 1/6. That'll be 2/6, 3/6, 4/6, 5/6, 6/6, and so on. That'll be 10/6, and so on. Now we see that there's an overlap. Okay, that this number here, that B is calling 2/6, and this number here, which A is calling 1/3, are really in this exactly the same position. We can see that because each one of these 6 pieces is exactly equal, and so 2 of them here, and 2 of them here, and 2 of them here subdivide things into 3 equal pieces. So every second one is a subdivision just as the same as the A subdivision. So what A is calling 1/3 is the same as what B is calling 2/6. So I'm writing that 1/3 is the same as 2/6. They represent the same point. And I should say it's because 6 and 3 are related. 6 happens to be 2 times 3. That's the reason why these 2 divisions overlap. Okay, so 1/3 is exactly the same as 2/6, and the 2/3 is exactly the same as 4/6. What's 5/3 on scale A is 10/6 on scale B. So 5/3 is the same as 10/6. The 11/3 here is the same as the 22/6 there. And the number 5, which A was writing as 15/3, is written by B as 30/6. So there's an important pattern here that we have to be aware of. How to go from this fraction to this fraction. In each case, the numerator and the denominator have been multiplied or divided by the same number. Okay? So to go from here to here, we've just multiplied the numerator and the denominator by 2. The 2 in the numerator means that we're taking 2 of them. And the 6 in the denominator means that we're taking things which are half as big as the 1/3. So since 1/6 is 1/2 of 1/3, 2 of them make 1/3. That's the basic reason why it works. But we don't have to draw all this scale in order to see that this fraction is the same as this. We just observe that if we multiply top and bottom here by 2, 5 times 2 is 10, 3 times 2 is 6. So these are just 2 different names for the same fraction. Or we sometimes say that these are equivalent fractions. Okay, it means they're equivalent ways of writing the same actual number. And there's no reason why we couldn't find more ways of writing a given fraction. So for example, instead of writing 5 over 3 equals 10 over 6, we could have multiplied top and bottom by 3 to get 15 over 9. That would be exactly the same fraction and have exactly the same position on the number line. Or 11 over 3, we could multiply top and bottom by 7 to get 77 over 21. That would be exactly the same position on the number line. So what we're saying is that if we take 11 thirds, we take 1/3 and we take 11 of them, that's exactly the same as what you get when you take 77 1/21ths. 1/21 is 1/7 of 1/3. So if you take 77 of them, it's the same thing as you get when you take 11 1/3. But we don't always just go from here to here. We also want a lot of times to go from here to here. Okay? In that case, it amounts to dividing the top and bottom by the same number. So if we start with 22 over 6 and we want to think, well, how can we simplify that? We note that top and bottom are divisible by 2. So if we divide top and bottom by 2, we get 11 and 3. Multiplying top and bottom by 2 gives us an equivalent fraction. Dividing top and bottom by 2 gives us an equivalent fraction too. It doesn't have to be dividing by 2, it could be dividing by 3. So for example here, if we took this one here and we divided top and bottom by 3, what would we get? We get 10 over 2. Is 10 over 2 the same thing? Is this also equal to 10 over 2? Well, yes it is. That would be in a different scaling system with a half. 10 halves also equals 5. There's a lot of different numbers, different ways of writing the same number. It's one of the things that makes fractions difficult to work with, is that we have to be aware of these equivalent ways of writing the same fraction. It's very important in algebra to understand if we multiply the numerator and the denominator by the same number, then the actual fraction is not changing. We're not changing the position of the point that we're talking about. And conversely, if we divide the numerator and the denominator by the same number, then the position of the point is not changing. Of course, if we took one of these, like 2/3, and we multiply the top by, say, 2, and we didn't do anything to the bottom, so we got 4/3, well, then of course the thing would be changing its position. It would be moving. But exactly doing the same to the numerator and the denominator means that it doesn't change. Very important to remember that. All right, good. So we've had a lot of review. I hope it's been mostly familiar, but I hope also that some of you will benefit from having the presentation. You will have learned how to think about the positions of fractions on the number line and equivalent ways of writing down a given fraction. So let's have a bit of practice. All right, so it's very important for us to solidify our understanding by doing some practice in mathematics. Hopefully in a book with pencil or pen and paper. So the first question is, on a number line, find the positions of these fractions. Okay, so how are you going to get a number line? Well, one way is to make one using a ruler. Another way is to use a piece of graph paper. Okay, a very friendly thing for a Year 9 student. So hopefully you will have a book somewhere that has some graph paper in it, and the graph paper is naturally subdivided into little pieces with all the little squares, and you can use that to mark off a number line. Okay, and you can decide, where you're going to space the 0, 1, 2. It doesn't have to be one line right after the other. You can space them regularly. Maybe every fourth one is an integer. 0 to 1, 1 to 2, 2 to 3, and so on. Okay, so you make yourself a nice number line, and then you try to figure out where do these various fractions, or rational numbers they're sometimes called, where do they fit in the number line? And which of these are the same? So some of them are the same. And which two are exactly 1 apart? So there's 2 of them that are exactly separated by 1. Okay, in question 2 we have various equations, and you have to fill in the blanks. So I'm going to do the first one for you. So 3/4 equals something over 8. What is the something? Well, how do we get an equal or equivalent fraction? We have to multiply top and bottom by the same number. What could we possibly be multiplying by to get the 3/4 into something eighths? Well, obviously we're multiplying by 2. Multiplying by 2 takes the 4 to the 8. And if we multiply the denominator by 2, we have to multiply the numerator by 2 if we want it to be equal. So that question mark has to be a 6. 3/4 is the same as 6/8. Somebody asks you, would you rather have 3/4 of a pie or 6/8 of a pie? You should shrug your shoulders and say, I don't care, it's the same. If you divide the pie into 4 equal pieces and you take 3 of them, you're getting just as much pie as if the person divided the whole thing into 8 pieces and you got 6 of those 8 pieces. It's another way of thinking about it. Okay, so there's some similar problems. And the last one, plot on a number line to find larger value. So here are 2 fractions, a little bit bigger. And I want you to sort of figure out where they are on the number line and try to figure out, well, which one of these is bigger? Maybe they're pretty close. Can you do a reasonably accurate diagram to convince yourself that this one's bigger or this one's bigger? And the same for those, and the same for those. All right, so we've had some review. Very important to feel comfortable with fractions and to have a good sense of where they fit on the number line. Of course, that's not the end of it with fractions, is it? We still have to talk about the operations. So very important for us to get a grip on the arithmetic of the number line. I hope you'll join me for that. I'm Wildberger, and we'll see you next time.